In our previous video, we looked at the graphs of sine and cosine, and we noticed that those graphs repeated every 2 pi, and we referred to that as the period. But let's define periodicity. A function, f, is said to be periodic if there exists, and that's a symbol for there exists, a p, this means such that f of x plus this value p is equal to the original function f of x for all x in the domain. So it has to happen over and over and over. It can't just happen once. P is called the period of f. In terms of sine and cosine, graphically, we already saw that the sine of x is equal to the sine of x plus 2 pi. If you picture on the unit circle, we come back around to 2 pi every time. And likewise, the cosine of x is equal to the cosine of x plus 2 pi. Therefore, we say that the period of both sine and cosine is 2 pi. We can use this information to then determine the periods of secant, cosecant, tangent, and cotangent. Remember, let's start with secant. Secant of x is 1 over the cosine of x. So if we start with secant of x, we know that that's equal to 1 over the cosine of x, but we just stated that 1 over the cosine of x would be equal to 1 over the cosine of x plus 2 pi, and based on the definition of secant, that would be equal to the secant of x plus 2 pi. So the period of secant is also 2 pi. Remember that secant is not necessarily defined for all x. Anywhere that cosine is 0, this would not be a true statement. The same method can be used to prove that cosecant is going to have a period of 2 pi, but what about tangent and cotangent? Well, we may want to think, well, it must be 2 pi again, but remember that if we have some angle, we talked about earlier that the tangent of that angle is y over x. So tangent is going to be positive anytime y is greater than 0 and x is greater than 0, or anytime y is negative and x is negative, which may indicate to us that this period is going to be reduced some. And this tells us then that our tangent of theta, or x, let's go ahead and use x, is going to be equal to the tangent of x plus pi as we move back into those quadrants where both x and y are positive or both x and y are negative. So the period of tangent is actually equal to pi. An additional definition that we need to make for this section that you may have heard before is the idea of even and odd functions. Now, we talked about end behavior in one of our first sections where you looked to see if both end behaviors were going in the same direction or opposite direction depending on if an exponent was negative. But today we're going to define what are called even and odd functions. And the way we do this is we say that if some function f of x is equal to f of negative x, the function is even. And if negative f of x is equal to f of negative x, the function is odd. And this does relate to those exponents that we talked about with end behavior, because if you consider a parabola, that is an even function, because when I plug in, say, x is 1, I get 1 squared if this was f of x is equal to x squared. And when I plug in negative 1, I get the same value. In contrast, something like a cubic function that looks like this, if I plug in, if f of x is x cubed, when I plug in 1, I get 1. When I plug in negative 1, I get -1, which is the negative of the original f of x. Notice here that even functions are symmetric to the y-axis, and odd functions are symmetric to the origin. If you go back and look at your graphs of sine and cosine, you're going to see that sine is symmetric to the origin. Thus, sine is odd, and cosine is symmetric to the y-axis. So sine is even. And what statement this allows us to make is that the sine of x is going to be equal to the sine, the negative sine of x is going to be equal to the sine of negative x. Cosine of negative x is going to be equal to the cosine of x, since it's even. And the tangent of negative x is equal to the negative tangent of x. In other words, we have sine is odd, cosine is even, and tangent is odd. This directly translates to their reciprocals. So cosecant, negative cosecant of x is equal to the cosecant of negative x. So cosecant is odd. Secant of negative x is equal to the secant of x. Thus it is even. And the cotangent of negative x is equal to the negative cotangent of x, which is odd. Now that we have this concept of even and odd functions, we can use this to help us prove and describe the transformation of cosine from sine. If you remember looking back at the graphs, cosine and sine were just shifted from each other. And so what we want to prove is that the cosine of x is shifted to the right by pi over 2. If you remember from things like parabolas, when we did y equals x minus 3 squared, this told us that it was shifted 3 to the right. And likewise here, we're trying to show that cosine is sine shifted to the right by pi over 2. Well, let's consider, first of all, just the idea of pi over 2 minus x. And if I add x to that, I get pi over 2, because you'll notice these two things cancel. Well, since pi over 2 minus x plus x equals pi over 2, by definition, we know that pi over 2 minus x and x are complements, because if you remember, complements add up to 90 degrees or pi over 2. This then allows us to use those cofunction identities that we looked at in a previous section. If we take then the cosine of pi over 2 minus x, I can rearrange that to the cosine of negative pi over 2 plus x, because remember, the cosine of x is equal to the cosine of negative x, since it's even. And all I've done is distribute a negative to both of these. Now, if I rearrange that, this gives me the cosine of x minus pi over 2, which based on those cofunction identities from the previous section, we know equals the sine of x.